In the last video, we introduced the concept of the average rate of change. So if we have some value y expressed as a function of x, then the average rate of change is the change in y over the change of x, right? And so if you look at a graph of f of x, then it's just the slope between 2 points on that graph of f of x, right? So if we take 2 points at x equals a and x equals b and calculate the rise over run, the change in y, which is the change in the value of the function, over and divide it by the change in the x, which is just that b minus a, then we get our average rate of change, which is the slope of that line connecting those 2 points. Okay, that line is sometimes called the secant line. All right, so now in this example, we're going to look at a particular application of average rate of change where our function is a function for the change in position. It's the function for position over time. Okay, so essentially distance over time. So our function is for distance, gives us distance over a time period. All right, so and when we calculate the average rate of change for a function that gives us distance, in terms of time, that average rate of change is average velocity. Okay, so this is just a specific case of average rate of change. Okay, so in this example, we have a watermelon that is dropped from the roof of a building that is 125 meters tall. And we're given a function, a formula for this function of the height of the watermelon versus time. All right, so you can see we have y equals 125 minus 5t squared. All right, so when t is 0, which you would expect, t equals 0, we're at the top. We haven't dropped, we're just dropping it. T equals 0. And so the watermelon is 125 meters above the ground, and then it looks like as time goes on, the distance from the ground, the height of the watermelon, decreases, right? So the distance from the ground decreases until eventually it hits the sidewalk below and splatters. So first thing is just to graph this function. So let's do that. So like I said before, initially when this watermelon is first dropped, it's 125 meters above the ground. So looks like we're going by 10. So let's put 125 at 0. We're at 125 meters above the ground. And then we can calculate the other points. Now I could make a table of values, or I can just do the calculations and then plot those points. So when t equals 1, right, we have 125 minus 5. So we have 120, right? So I'm just going to plot that point. And again, I'm just going to plot these points. And there we go. I've put in these different values for t equals 1, t equals 2, t equals 3, and then put it into the formula for my height above the ground, and then I've just plotted those points. So, and I've labeled them so we can refer back to the values. So the next question asks us to find the average velocity between t equals 2 and t equals 3. Okay, so remember the average velocity is just an average rate of change. All right, it's the change in y over the change in t over this time period from 2 to 3. So it's going to be the value, the height at 3, so it looks like 80, minus the height at 2, which is 105. And then we're going to divide that by the time difference, which is 3 minus 2. All right, so what do we get? Now notice we're going to get a negative because we're subtracting a large number from a smaller number. The denominator is just 1, so we get a negative 25 meters per second. Okay, what does that negative mean? What's that telling us? The negative is just telling us that the height above the ground is decreasing, right? It's getting closer to the ground because the watermelon is falling, right? So we could interpret this as 25 meters per second in the downward direction. Okay, So it's falling downward. So the negative is just indicating that it's falling downward and that the height of the watermelon is decreasing. All right, on the graph, show the average velocity in part A as the slope of a line between 2 points. So my hand isn't quite steady enough to do that freehand. So I've drawn a little line segment in here, a little red line segment. And that line segment, the slope of that line segment would be the average velocity between those 2 points. All right, now we got to do some work down here. It says use the formula to find the average velocity for each interval. Okay, so we have various time intervals. Okay, and we want to calculate the average velocity at each of those times. Okay, now we've done 2 to 3, so I can fill that in, right? That was a negative 25 meters per second. Okay, now I've just got to do that over and over again for these different time intervals. Now notice that the left-hand side of my time interval is always 2, and the right-hand side of the time interval is just getting closer and closer and closer to 2. So let's do those calculations. All right, so there we go. I've done it offline. You don't need to watch me do all those calculations. But I mean, essentially what I did is I just plugged the left and right time values into the function. Now, again, like I said, the left hand side is always 2, so my f of 2 is always 105, right? And then I'm just varying the right hand side of the time interval, and then I'm calculating. So like 80, right? In this particular case, 80 is f at 2.5, right? I just plugged it into that equation, and then subtracted 105, and then divided it by 2.5 minus 2, which is 0.5, right? It's a 0.5 second time interval. All right. So there we go. Now you can see something happening here, right? You can see that, you know, as my time interval gets shorter and shorter, my velocity seems to be approaching some value, right? Now, what is that value? So that's part E. Part E is asking, what's the best estimate for your velocity, for the velocity of the watermelon at 2 seconds? At 2 seconds. All right. Now, this is a different concept, right? We've been looking at average velocity over a time interval, right? So we're looking at the change in distance over the change in time. That's what we did to calculate all of these values. Those are average velocities. But now we're looking at a different concept. We're looking at the velocity at a particular time, right? With no time interval, all right? But you can see what's happening as my time interval gets shorter and shorter and shorter. I would estimate that the velocity of the watermelon at 2 seconds looks to be about minus 20 meters per second. That's what I would, if I round that off. It looks like that's what it's approaching as the time interval gets shorter and shorter. Okay, so just like in my car, when I'm driving down the road, my speed may vary over time, but when I glance down at my speedometer, I can see what my speed is. I can see what the speed is at any given moment, at any given instant in time. And so that is our next big concept in this section, which is instantaneous velocity, which is the velocity at an instant in time. All right, so let's go to this next thing here. The instantaneous velocity of an object at time t is defined to be the limit of the average velocity of the object over shorter and shorter time intervals containing that time. Okay, so in this case, our time is t, and we're looking at shorter and shorter intervals of time near t equals 2, and we can see that it appears that our velocity is approaching negative 20 meters per second. So it's falling at a rate of 20 meters per second in the downward direction at t equals 2. Okay, so that's the big idea here. And notice the word limit, right? That's the kind of the title of this section is the idea of limits. And so we're looking at the limit as that time interval approaches 0. So as that time interval approaches 0, or those two times get closer, the time intervals, those two ends of the time interval get closer and closer together, our instantaneous velocity looks like it's going to be negative 20 meters per second. So 20 meters per second in the downward direction.